In this video, we're going to see the last type of stereoisomer called an enantiomer. So remember, stereoisomers are when the molecules have the same molecular formula. They'll actually also have the same bonding sequence, so they're bonded in the same order, but they differ in their 3D orientation. The first type that we saw was called a diastereomer. The diastereomer is only for alkenes. So when you have the double bond, then you can put the groups on double bonds in different ways. So you can have them both in the same, both above the double bond, or one above and one below. So cis versus trans. And the last type is our enantiomer. The enantiomer is also a stereoisomer, except it doesn't involve a double bond. Rather than involving a double bond, it involves a carbon that has 4 different things bonded to it. So generally, we're looking at tetrahedral carbons. Or in other words, sp3. So if we look over here, we have 4 different things bonded to this carbon. So this is a carbon over here. This is a carbon over here. And what I want you to notice is that right here we have a mirror. So here I'll put, let's say, a Cl, an H here, a Br here, and an F here. I'll put the F here as well. I'll put the Br here over here. It's the red one. The Cl over here and the H here. And so what I want you to notice is that these 2 molecules are mirror images of each other. They have become non-superimposable mirror images of each other. What that means is they look the same, but because they're mirror images and they're non-superimposable, you can never make them fully match up on each other. So if you look at your left and right hand, they're non-superimposable mirror images. If you try to fit your left hand into your right hand, you'll never be able to do that with them facing the same direction. Your thumb will never match up with your other thumb. That's considered non-superimposable. So this actually gives them different properties in the body and chemically speaking. These 2 things are called enantiomers. But to have enantiomers, you need to have a carbon with 4 different groups connected to it. If you have only 3 different groups connected to it, it won't work. So you have carbon with 4 different types of atoms or groups connected to it. When I say groups, it could be CH3 as a group, for example, connected to it. So CH4 could not have enantiomers. But something like this, CHBrFCl, can, because you have 1, 2, 3, 4 different things connected to the carbon. And the way you draw it is you show essentially the molecule as if it's looking in a mirror. And so the Cl's would face each other. The F over here would be on the same side. The Br would be facing away from each other, and the H over here would be facing each other as well. But that shows their mirror images to each other. And a carbon that has 4 different groups on it has a special name. We call it a chiral carbon. So a chiral carbon is a carbon that has 4 different groups attached to it, and it's tetrahedral. So chiral carbon, tetrahedral or sp3 carbon with 4 different groups. And as long as you can identify a chiral carbon in your molecule, then you know that your molecule can have enantiomers. And that gives even more diversity. So we've now seen diversity in organic molecules can exist because of the different isomers. From similar subsets of atoms, you can make different molecules by simply changing the bonding arrangement. You can have constitutional isomers or structural isomers, where we have the same molecular formula, but we bond things in different ways. We can have stereoisomers, also called geometric isomers, where you have the same bonding arrangement, but different arrangement in space, 3D arrangement. So same bonding sequence, I should say, but different 3D arrangement. And that could be a diastereomer, which is a cis or trans about a double bond, or an enantiomer, which is the mirror image molecules as long as you have a chiral carbon with 4 different groups on it. So here's the mirror, and you can see that you can never really make all these atoms fit into each other like the hand in a glove. And that's because they're opposite. That's because they're mirror images of each other and are non-superimposable, and they will have different properties overall. A great video to watch is the Evil Twins video, which is linked in your handout and in your calendar as it goes over the concepts of enantiomers in more detail. So we've seen how organic molecules can experience such a great diversity and variety from such a small subset of things like only carbon, hydrogen, and a few other handful of atoms that we see.